Hi there. In this video, we're going to be talking about topic 6.1 of the AP Chemistry curriculum, endothermic and exothermic processes. So when we talk about endothermic and exothermic, we can look right at the words themselves to see what it means. Endo, meaning inside, and thermic, meaning heat, so heat going inside a process, or exothermic, where exo means outside, and thermic still means heat, so heat going outside the process. And when we talk about a process, we're talking about a few different things. A process could be heating or cooling of something. We could be talking about a phase change, and so something going from one state of matter to another state of matter. Or we could be talking about a chemical change, or maybe we could be talking about dissolving something. So all of these are types of processes that we're talking about in chemistry that are either endothermic or exothermic processes. So typically, if you have a temperature change in a process, that means that there was an energy change in the process. So energy either went up or energy went down. So when we talk about endothermic and exothermic, we need to define two different things. We need to define our system, and we need to define the surroundings. When we talk about system and surroundings, system is whatever you're interested in. So what substance are you heating or cooling? That would be your system. What substance is going through a phase change? That would be your system. What are the substances in a chemical reaction? Those substances would all be your system. When something's dissolving, what substance in the water is dissolving? That would be your system. The surroundings would typically be everything that is not your system. And just as a note, your system plus the surroundings is called the universe. That comes into play like in the law of conservation of energy, which all of this depends on. Energy can't be created or destroyed in the universe, but energy can be transferred between places in the universe. So energy can go from the system to the surroundings, or energy could go from the surroundings to the system. So since we're talking about we're talking about heat, we are specifically going to be talking about heat transfers here. And the symbol for heat is Q. So you're going to see me using Q's a lot here. And that's what we're talking about. So Q means heat. So for an endothermic process, when we talk about an endothermic process, that means that heat is going into your system. Endo meaning into or in. So energy is going into a system in an endothermic process. Where is that energy coming from? Well, it's coming from the surroundings. So anytime you have an endothermic process, whether it's just a temperature change of a substance, or whether it's a phase change of a substance, or whether it's a chemical change or dissolving, if energy is going into the system, then that's an endothermic process. Energy goes from the surroundings to the system. And just as a note, the heat of the system is equal to the negative heat of the surroundings, because the heat is losing energy, so we call that negative, and the system is gaining energy, so we call that positive, which is another important sign convention when it comes to thermochemistry. Positive always equals gain, and negative always equals loss. So did the system lose energy or gain energy? Gained heat, so it's a positive heat. So that's an endothermic process. What about exothermic? Well, again, from the point of view of the system, and everything is about the system, exo means leave, kind of like an exit. So if your system loses heat, heat goes away from your system to the surroundings, then that is an exothermic process. Your system is losing energy and your surroundings is gaining energy. And the amount of energy, the magnitude of the energy is exactly the same. They do have opposite signs, but the amount of energy is exactly the same for the system and the surroundings, because the law of conservation of energy says you can't gain or lose energy. It just can be transferred from one place to another. So that's some conventions about the signs of energy and heat losses or heat gains. Now let's just talk a little bit about specifically what's going on. So if you're heating or cooling a substance, let's say that you have a pan of water and you heat it up. So that's fire. I know that it's green, but okay, it's fire. Anyway, you're heating up the water. The water is, molecules are moving faster and faster and faster. Are they gaining energy or are they losing energy in this process? Hopefully you said gaining energy because they're moving faster. So that would be an endothermic process. Heat is going into the pan to heat it up. So what if you cool something down? What if you turn the heat off? You turn the heat off, and now the hot water is going to start cooling. When it cools, is that an endothermic or exothermic process? Well, the water molecules are slowing down. That means they're losing energy. Where's the energy going? It's going into the surroundings. And so that's an exothermic process. So heating is endothermic, cooling is exothermic. What about phase changes? Let's just think about the same pan of water. If we go from liquid water into gaseous water, does the gas have more energy or less energy than the liquid water? Well, each water molecule is moving faster as a gas than as a liquid. That means it gained energy. So boiling is an endothermic process. You have to add energy to a liquid to make something boil to go to a gas. So boiling is an endothermic process. What about condensing? What if the steam all of a sudden condenses back into water? Well, do the water molecules speed up or slow down when they condense? Hopefully you said that they're slowing down as they condense, they're forming bonds, and so they are going to release that energy, which is an exothermic process. So as steam turns back into a liquid, condensation is an exothermic process. So again, think about what's going on with the molecules in phase changes, and that will help you think about whether something's endothermic or exothermic. Okay, if molecules are speeding up or bonds are being broken, then that means it's endothermic. If bonds are being formed or if molecules are slowing down, that's an endothermic process. So let's talk about chemical changes since we're talking about bonds. Breaking bonds is always endothermic. It always requires energy to break bonds. So breaking bonds, always endothermic. That is a really important point. Forming bonds, then, is the opposite. So what is forming bonds going to be? Always exothermic. Always, always, always. Breaking bonds is always endothermic. Forming bonds is always exothermic. And in almost all reactions, you have to do both. You have to break some bonds and you have to form bonds. For instance, let's say burning gasoline in your car engine. C8H18. Gasoline is octane, because there's 8 carbons. And if you take this liquid gasoline, form it into little droplets of gasoline, and we burn it with oxygen, which is a gas, it forms carbon dioxide and water. If we balance this whole thing, we get 2, 25, 16, and 18. And so if you burn gasoline, you have to break all of these bonds between the carbons and hydrogens and the oxygens. All these bonds have to be broken, and then all of these bonds get reformed. So we have bonds broken. Is that endothermic or exothermic? Breaking bonds is always endothermic. So heat or energy has to go in to break all of these bonds. And then when these new bonds are formed, energy is going to be released. And so we have this balance between energy going in and energy coming out of this chemical reaction. And almost all chemical reactions require bonds to be broken and new bonds to be formed. So the question is, how do we know if this is going to be an exothermic reaction or endothermic if both things are happening, if it's both endothermic and exothermic? Well, the question is magnitude. Is the heat going into the reaction greater than or less than the heat coming out? If the heat going into the reactants is greater than the heat coming out of the products, then this is going to be an endothermic reaction. And later we're going to talk about delta H, enthalpy changes, rather than heat, But for right now, we're just going to use heat in this particular process. So if the heat going into the reactants is greater than the heat coming out of the products, then more energy went in than came out. That's endothermic. The overall reaction will be endothermic. And so breaking the bonds took more energy than energy that was released when new bonds were formed. What about if Q of reactants is less than Q of the products? Well, less energy went in to break the bonds than came out of the reaction. This would be an exothermic reaction. And so more energy came out than went in. Now I want you to think about burning gasoline. If I burn some gasoline, I react gasoline with oxygen, do you think that's an endothermic or exothermic reaction? Hopefully you said exothermic. A lot of heat is produced. That's why your car gets so hot, or one of the reasons your car gets so hot. A lot of heat energy is released. And so for this particular reaction, the energy of forming the carbon dioxide and water molecules is greater than the energy going in to break the gasoline molecules. And that's good, because if it took more energy to burn the gasoline than energy came out, you couldn't use this to power your car. That energy that comes out of the reaction is what we use to power your car. Not the heat so much, more of the expansion of gases, which is work. But we're not going to talk about work here, but that is another thing that could be happening here, is heat and work can be produced by these expanding gases. We went from 25 moles of gas to 30 moles of gas. So the gas is expanded, and that's what pushes the pistons, which powers your car. So some of the energy released by this reaction is work, which powers your car, the expansion of those gases. Okay, so we've got endothermic versus exothermic. We've talked about bonds being broken and formed. The last thing I just want to talk about is forming solutions. When you form solutions, this also can be endothermic or exothermic. So if I have some water and I want to dissolve some salt in the water, the sodium and chloride ions have to break apart and be attracted to the water molecules in order for this to happen. And so is the energy required to break the sodium chloride apart and the energy released when the sodium and chloride are attracted to water molecules? It's the same thing as these chemical reactions. Did it take more energy to break the bonds, or was more energy released when the water ion, the dipole ion force was formed when they dissolved in water? If the energy released by these attractions is greater than the energy breaking these bonds, it'll be exothermic. If the energy to break the bonds is greater than the energy released when the ion water attractions are formed, then it'll be endothermic. You might be asking, why would something dissolve if it's endothermic? Why would something dissolve if it takes more energy to break the crystal apart than is released by the ion dipole attractions of the water? And the answer there is entropy. Entropy is randomness, and we're not going to talk about entropy here. That's for a much later lesson, but that's why it could happen. But dissolving processes can be endothermic also. In fact, ice packs, chemical ice packs are this process. Ammonium chloride is dissolved in water, and it's extremely endothermic, cold enough to make an ice pack and actually freeze water and help whenever you've had an injury on the field. So anyway, that's it. That's all I want to talk about right now. If you have any questions about any of these concepts, please talk to me. I'll be happy to help you out. Good luck.